Well, hello there. Welcome to this series of favorite integrals. Um, Today I want to consider the integral of the natural logarithm of the sine, where the variable runs from 0 to pi. On the right, I have included a graph of this function, and you must notice that the integrand is always negative except for one value, that is pi divided by 2. And this integral will have a negative value as well. So that's a test afterwards. If we come up with a negative, if we come up with a positive value, we can be sure that we have done something wrong. How are we going to calculate this integral? Well, the amazing thing is that we can use a lot of symmetries to calculate it, and a simple identity from trigonometry to do so. First of all, we notice that we can double the angle. We can replace x with 2x, where the new x is, of course, running from 0 to pi divided by 2 instead of 0 to pi. But if we've got a differential of 2x, of course, we can put the constant in front, because the differential 2x is equal to 2 times the differential of x. So this factor 2 is easily accounted for in this way. So we've got 2 times the integral of from 0 to pi divided by 2 of the natural logarithm of the sine of 2x dx. Now we're going to apply a trigonometric identity, that is, the sine of 2x equals 2 times the sine of x times the cosine of x. And if we have a number of factors under the logarithm sign, of course, the logarithm turns these factors into terms. Logarithms turn multiplication into addition. So if we've got the natural logarithm of the sine of 2x, that is the natural logarithm of 2 times the sine of 2x times the cosine of x, we have a number of terms in this way, of course. The factor 2 is now accounted for in a separate integral with just a constant under the integral sign. That is 2 times the integral for x running from 0 to pi divided by 2 of the natural logarithm of 2. Now we've got 2 times the integral where x is running from 0 to pi divided by 2 of the logarithm of the sine, and the same for the logarithm of the cosine. Now, of course, we know that the cosine takes on exactly the same values as the sine in the region of 0, between 0 and pi divided by 2, albeit in a different direction, because the cosine equals the sine of pi divided by 2 minus the constant. So these last two terms can be put together to arrive at this identity. We have evaluated the first integral as pi times logarithm of 2. Then we've got 2 times the integral of the logarithm of the sine plus 2 times the same. So now hang on. We've got this. We now have that the original integral should be equal to pi logarithm of 2 times plus 4 times the integral of x running from 0 to pi divided by 2 of the logarithm of the sine. Now, if you take a look at the diagram, you will notice that there is a symmetry um, because the function takes on exactly the same values after pi divided by 2, between pi divided by 2 and pi. So instead of writing 4 times the integral of the logarithm from 0 to pi divided by 2, we can also write 2 times the integral of the whole region. So now we end up with this. The original integral equals pi logarithm of 2 plus 2 times the original integral. That is the integral of x running from 0 to pi of the logarithm of the sine. So now we end up with this identity. We have the original integral must be equal to pi logarithm of 2 plus the 2 times the original integral. And as a result, we now have that the original integral must be equal to minus pi logarithm of 2. So now we have arrived at the outcome of this integral. And we used only a bit of trigonometry and some properties of the logarithm, and we used some symmetries, which is fairly amazing. Now, from a practical point of view, of course, we have only, that is a bit of an engineering remark that I'm making now, we've only replaced one infinite process, that is evaluating the integral, with another one, because on the left we have an integral which involves an infinite progressive evaluating functions and so forth, because the logarithm itself is a transcendent function, and of course the process of integrating itself is infinite. But on the right, we also have an infinite process going on, because we can only approximate the value of pi and approximate the value of logarithm of 2. And that means that from an engineering point of view, we really haven't gained a lot by replacing the integral with the value on the right. But from an analysis point of view, of course, we have done a lot, which is quite amazing. I hope to be able to present you some more favorite integrals in more videos. That's it.